So state Newton's universal law of gravitation. This is basically given by this formula in your data booklet, that your force is proportional to the product of the masses, m1 and m2, and inversely proportional to the distance between them squared. So that's Newton's law of universal gravitation. The G is our gravitational constant, universal gravitational constant. You can find that in the front of your data booklets. It's about 6.67 times 10 to the negative 11, the value of that. It's actually quite a very small constant. We're going to compare it to our Coulomb's constant over there, which you're going to see is much more. But we have this that it's the product of the masses divided by the radius squared. Now, a lot of this, when dealing with problems with these, is that you need to be able to work with the proportions. So what happens when you double the masses and halve the radius and so forth? You need to be able to work with those proportions. So then we get this idea of defined gravitational field strength. Now, the gravitational field strength is the force per unit mass that a mass will experience in the gravitational field of another mass. So if I, for instance, got, let's just use the Earth. If you've got the Earth here, mass of the Earth there with a certain radius RE, and if you have a mass on the Earth, let's call that M1, then the force between M1 and ME will be given by Newton's universal law of gravitation. ME M1 over RE squared. It'll be like that. Now, the gravitational field strength is the force per unit mass. So you're actually dividing this force by the mass that's experiencing the force. So if we want to find the gravitational field strength of the Earth, we're going to divide it by the mass that's experiencing that force of the Earth. So we're going to divide it by m1 on both sides, and we get this over here, this F divided by m1 is, we give the symbol g. That is actually obviously our acceleration due to gravity. It's when we put these values in, for the mass of the Earth and the radius of the Earth, and we put it into that equation, it comes out at 9.81. So 9.81 is our gravitational field strength, is 9.81, and we can work that out. Obviously, if I've got a mass of 1 kilogram, it will experience a force of 9.81 newtons. If I've got a mass of 2 kilograms, it would be double that. This is a force per unit mass. All right. Now, obviously, we can see that this also relates to Newton's second law, because force is equal to mass times acceleration. So acceleration is a force per unit mass. Okay. Now, there are two ways to actually find the mass. We can either use our law of gravitation. We call that the gravitational mass. The gravitational mass. So we can use that law to find the mass of an object. We can determine the force between two masses, know the distance between them, and know the mass of one of them, and be able to work at the mass of the other. We can also find the mass according to Newton's second law. This is called the inertial mass. Now, it turns out that when we calculate the mass of an object, due to these two methods, either using Newton's second law or Newton's universal law of gravitation, it works out to be the same value. So we get the same mass using either one. And that's why also we can actually equate these two together. That our force is equal to ma, and our force is equal to Newton's second law, Newton's universal law of gravitation. So we have these two formulas which you need to be able to use. Now, in working with this, you need to be able to determine the gravitational field due to one or more point masses. So for instance, if I've got, say, mass 1 there and mass 2 there and say mass 3 there. Now, the force of gravitation is always an attractive force, so there's going to be a gravitational field strength. If I'm looking at M3, there's going to be a gravitational field strength due to G1, and there's going to be a gravitational field strength due to G2, due to mass 2, which I'll call G2. Now the combined effect on that would be the vector sum of those. So I would have to find the sum of those. This would be the combined gravitational field strength of 1 and 2. Okay, so it will be the vector sum of the two. It would. So you would work out this G1 using the formula that big G M1 over R1 squared. All right, and G2 would be big G M2 over R2 squared. And once you've worked those values out, you would add those vectors. You would add the G1 vector and the G2 vector. They're at different angles, so you would complete the parallelogram and get your combined gravitational field strength. Okay, and when we look at a surface of the planet, or the gravitational effects due to a planet, we assume that all its mass is concentrated at the center. So if we have, for instance, the Earth, we have the mass of the Earth. We assume that all that mass is at the center of the Earth, and we look at it that it has a certain radius RE.